Hey, welcome back everybody. It is great to see you once again. As you can see, we're going to be talking about Taylor series and error. Now you know where we've been, right? We've been talking about adding together a lot of functions over and over and over. I mean a lot of functions, and in fact an infinite number of functions. And what we've seen is that if we do that, on some domain these things converge to yet a more complicated, possibly more interesting function. Now the problem with this whole thing is this. We don't have time to add together an infinite number of things. And so frequently what we will do is we will stop. We will truncate. We will quit adding things together, and that will incur some amount of error. And so today the conversation is going to be about this error that we incur when we truncate things. Now for the last couple of minutes you've been watching me talk and you've noticed this blue bat in my hand, right? And you're wondering, what the heck does that have to do with Taylor series? Well, what we're going to do is we're going to give you a couple of contexts to understand this error thing. And that's going to take us not only today's video, but the one after that and the one after that. So we'll talk about special relativity in the next video. And then in the third video, we'll talk about how we might be able to take this little baseball bat that my son owns and hit a ball, and how special relativity and Taylor series come into play, or not. So that's for the following video. So today, though, we just want to focus on the error and the theory behind the error as we talk about this sort of thing. So let's get started with a very specific function here that we can use to talk about this. And the function is this. F equals to 1 divided by root 1 plus x. So last time we talked about how we might build up the Taylor series for this function. And what we have to do is we have to have some sort of center of approximation. So in fact, we're going to use 3 different centers of approximation to construct the Taylor series, 0, 1, and 2. And then we'll see some similarities and some differences as we do that. And I think out of that, we'll begin to understand some of the broader picture behind the structure of the error. So let's first rewrite this slightly as 1 plus x to the minus 1/2. The reason that we need to do this is that when we put together our Taylor series, this requires the calculation of these coefficients c sub n, and each c sub n requires a derivative. Derivative 1, 2, 3, 4, up to the nth derivative. And we evaluate that at the center, and then we divide by n factorial. So we need a lot of derivatives is the bottom line. So let's go ahead and start taking derivatives of this thing, and then we'll begin to test our various centers. So as we do this, you'll see the first derivative come up, the second, the third, and in fact the nth derivative we have for you at the bottom of the screen. So let me point out a couple of things. Each time we take a derivative, we take the exponent and we bring it down and multiply out front. And then we do that again with minus 5/2, that comes out front. Minus 7/2, that will come out front. And when we do that, 2 things happen. We start to build up this 2 times 2 times 2 times 2 and so on, and that gets us our 2 to the n in the denominator. And in the numerator we have minus 1, which is an odd number, minus 3, which is the next odd number, minus 5, which is the next odd number. And so we build up the numerator here by minus 1, minus 3, dot, 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 2n minus 1 creates all these odd terms here. So what we're going to do now is we're going to take our 0 and we're going to substitute in to see if we can find each of the coefficients. So again, let's take a peek quickly at what the derivatives look like. We're going to put a 0 here, 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 and here so that we can calculate the coefficients defined by these derivatives evaluated at a equal to 0. And we can do that very quickly behind the scenes here. So we do. So our first Taylor approximation, T0, is simply the constant 1. And so you see before you a graph of 1 divided by the square root of 1 plus x in the first approximation. In the center here at x equal to 0, we see that we have very high accuracy. In fact, it's exact. But as soon as we move away from the center, error, error, lots and lots and lots. In fact, the further we go away, the bigger that the error gets. So we do what you always do, right? You add another term. 1 minus x over 2 is t sub 1. And the nice thing is we see more accuracy in a wider domain here. But we still have problems with error when we get away from the center. It's great close to the center, poor as we move away. And in fact, if we look at the bendiness of the function, how fast it's decreasing here versus how fast it's decreasing here, we can see that quickly on the left, we have pretty big errors very quickly. And so one of the things that we're noticing is that not only does the center of approximation matter, but also the inherent properties, what I'm going to call the bendiness of each function, impacts the error as well. So we can add more terms, more terms, more terms. And as we do this, we notice a third idea, and that is we have convergence only within a particular domain, and this particular domain happens to be between -1 and 1. So what do we have? We have this idea of a center of approximation. You see the blur that represents that. We see this rectangle that represents the interval of convergence. Close to the center of approximation, very high accuracy. Far away from it, very low accuracy. And we only converge within the interval, and we have no hope outside of that. So consequently, our interval of convergence is -1 to 1. And with a little bit of work, we can see that it does include the right endpoint of 1. Okay, that's one center of approximation. Let's shift the center of approximation from 0 to 1. Again, we'll evaluate each of the derivatives with 1 this time. We will stick that into our coefficient formula right here, and we will begin to generate our Taylor polynomial. So let's take a peek at what this thing looks like. The first term has changed from 1 to 1 divided by square root of 2. Again, very high accuracy at our new center. As we move further away, poor accuracy. The bendiness of the function happens to impact that here more than it does on the right. And then so we add more terms. Increasing the number of terms increases the accuracy. We keep doing that. And then something interesting happens here. We've only added 2 terms, but the domain of the accuracy is quite large compared to our previous Taylor approximation where we use a center of 0. And so somehow I think we're going to see that the center of approximation also impacts the interval of convergence, how wide this convergence might be. So we add a few more terms, and a few more, and a few more, and eventually, if we add enough, we will converge to the original function. But we can see that our interval of convergence seems to be somewhere over here, and it winds up and it ends somewhere over in here. And we have the same idea, high accuracy close to the center, but a broader interval of convergence. And in fact, the interval of convergence for the center at a equal to 1 is -1 to 3, and happens to include the right-hand endpoint, which would require some work to really pin down. So let's try one more center of approximation. A equals to 2. Again, substitute 2 into each derivative. The reason for this is that allows us to calculate each coefficient using our coefficient formula, and then we can roll out our Taylor approximation. We have a nice visual of this. We see that the first term has changed yet again. It's 1 divided by square root of 3. Our new center of approximation is over here. We add another term in order to get more accuracy. And with just a single more term, we see that we have really nice accuracy over a fairly wide domain right here. So shifting the center has increased the accuracy over a wider domain. But the further we get from the center, say we go to the left here, the worse that the error happens to get. And in fact, yet again, because we have a rapidly decreasing function here, the error is greater on the left relative to the center than it is on the right, where it is not decreasing as fast here. And we can continue to add more and more and more terms. And as we do this, again, we see visually that we have very high accuracy close to the center, poor accuracy as we go far away from that, and the interval of convergence is very wide. It happens to be between -1 and 5, including the right endpoint. So what do we have so far in this little experiment where we've run through different Taylor approximations at different centers? I think one of the things that we've seen is this. The number of terms matters. If we increase the number of terms in our Taylor polynomial, the better accuracy that we get. The second thing we've seen is that the accuracy is close to the center, poor as we move away from the center, So the location relative to the center of approximation impacts our accuracy. The third thing that we've seen is that the bendiness of the function, that matters. If the function is rapidly decreasing or increasing, that's going to have some impact on the error. And then the last little caveat that we have is that somehow the interval of convergence, the width of that, may be impacted by simply by changing the center in some fashion. So that's a nice visual, that's a nice qualitative understanding of what's going on, but we would really like to be able to understand this from a precise mathematical point of view. So in order to do that, I need to introduce some new notation. So here it is. Our function, and again, this function happens to be 1 divided by the square root of 1 plus x. This function happens to be equal to our Taylor polynomial, which we have just seen several pictures of for various values of n, plus a remainder term. And this remainder term, if we take the absolute value of that, happens to be what we're going to be calling our error. So we need to get some sort of handle on what the remainder term looks like. Again, keep in mind that the Taylor polynomial t sub n has a finite number of terms in it, which means all the terms that we get after we truncate are embedded somehow in this remainder term r sub n. In other words, there are an infinite number of terms in this. But as we can see from the next formula that's going to pop up, we have a single description here. In other words, this single term here, the n plus first term that comes after we truncate our Taylor series, this somehow contains an infinite number of terms of information. And it does it in a really special way. The first thing we pointed out with our error was that the number of terms matters. And here is how this is reflected in this remainder term. As the number n gets larger, n plus 1 factorial gets larger, and therefore the fraction gets smaller. In other words, the remainder decreases, just as we might expect, by increasing the number of terms. X minus a here is a measure of how far we are away from the center. And the larger this is, we raise that to the n plus first power, the greater this value will be, and therefore big differences in location from the center result in big errors. And the third thing that we see is that these derivatives, the n plus first derivative here, is our measure of the bendiness of the function. Lots of bends means high derivatives of some sort, which means bigger errors. Now this is a beautiful theoretical result. The problem is we've evaluated this derivative here at z. And z, in fact, is unknown to us. We don't know what it is. We only know that it happens to be between x and a. And a, again, is our center of approximation. And this is a problem. So in theory, this is beautiful, but in practice, what we're going to have to do is we're going to have to think about the worst case scenario for each of these derivatives. And so what we do is we cap each derivative with this capital M for max. M, in fact, is the max of the n plus first derivative, and we look at values in between x and a. So somehow, these kinds of problems boil down to asking ourselves a question, what's the worst case scenario? And that's where the M, the max, comes into play. So let's see how this might work with our previous example. 1 divided by the square root of 1 plus x. And we'll just calculate this at the center of a equal to 0. And to make our life a bit simpler, we'll use t sub 1, our first degree Taylor polynomial. And you can see that this is just a tangent line here. And we have a nice picture of what the error looks like at a point of our choosing. We'll just say we'll use x equal to minus 1/2 here. And we can see that the error looks like it's around 1/3 or thereabouts with this particular truncation of the Taylor series. So what we're going to do is we need to try to find out what does r sub 1 look like. And remember, r sub 1 is all the terms that we ignored, an infinite number of terms as a matter of fact. But we also have this very nice statement of the remainder that collapses these infinite number of terms into the single statement involving the second derivative, n plus 1 is 1 more than 2 here, divided by 2 factorial, and then we have x minus 0 squared gets us x squared. Again, the problem is we don't know where to evaluate the derivative. It's some unknown z here. We do know that z lies between negative 1/2 and 0, because negative 1/2 is our point of approximation. 0 is our center of approximation. So we substitute all of these values in. And so we know that x was negative 1/2 squared. We have 2 factorial here. We still don't know what capital M is. So we have to bound our second derivative. And we've got a nice statement of our second derivative here by considering what is the worst case scenario for values of z in between negative 1/2, our point of approximation, and 0, the center of the Taylor series. And so this is where you have to do a little bit more analysis of the second derivative. I can point out that it in fact is a decreasing function. We know that it's decreasing because as z increases, the denominator increases. And as the denominator increases, the overall fraction here decreases. So with a decreasing function, the maximum will occur at the left endpoint, on the left side of the interval, which is at z equals to negative 1/2. So the worst case scenario, in other words, the maximum of the second derivative, is going to be minus 1/2, and we therefore substitute that into our derivative formulation, and we have an expression for what m is. Take that, plug it into our error term here, our remainder term. It happens to be 3 times the square root of 2. And when we simplify all of these terms, we get a maximum error of 0.53033, on and on and on. In other words, again, this is the worst possible error that we could have. The actual error may be less than that. And in fact, it looks like it's a bit less. It looks like it's about 1/3 as opposed to 0.53. But what we have is the worst possible scenario for our error, which in most cases is the thing that you minimally want to take a look at. So what do we have for today? We've got this idea that anytime we have a Taylor series, we're probably going to truncate it. When we chop off an infinite number of terms, that means that the remainder or the error associated with that remainder is of importance to us. We have a nice formula for this remainder. You see it in front of you. And what we're going to have to do to manipulate this is to consider what choices for z will make this the worst. In other words, the biggest, because that's the worst case scenario. Well, you know what you got to do right now. You have some prep problems online. Go ahead and take care of those, and we will see you next time. Thanks for coming.